Alright guys, so yesterday we went over the math basis whenever we're dealing with a weak acid and a strong base. So we talked about it initially starts out at a lower pH, then we get into that buffer region before the equivalence point where we're still able to neutralize all of the added base. When we reach the equivalence point, we only have that weak conjugate base left over, and it is at a higher pH than 7 whenever it neutralizes, because we do have a strong base. It's going to be more of a basic pH at the equivalence point. And then remember, after the equivalence point, we have excess hydroxide. One thing that we can also gain from our titration curves is we can also find the half equivalence point. So this is the volume of titrant added that is half the volume of the equivalence point. So if the equivalence point is at 30 milliliters, the half equivalence point will be at 15 milliliters. One of the reasons that we look for this is at this half equivalence point, our number of moles of our weak acid and our conjugate base would be equal, meaning that our pH at that point in time would be equal to the pKa of our weak acid. And this yet again is because our ratio of our base to our acid at the half equivalence point, we would have the same amount of acid and base. So this would yet again end up being the log of 1 would end up being 0. So at that half equivalence point, the moles of acid and conjugate base are equal. So pH is going to be equal to pKa. This can be used to help us figure out which weak acid we're titrating if we do not know based off of that data. So the moles of strong base added would be half of the amount of moles of the original acid. So here's a basic acid base neutralization. So HA is our weak acid. Hydroxide is representing our base. Our anion is going to be that conjugate base that comes in. And then we have water. For example, if we started off with 0.5 moles of weak acid, half of that would end up neutralizing, so we would have 0.25 moles of base. And if that reacts, we end up with the same amount of weak acid and weak base. So whenever we plug it into the Henderson-Hasselbalch equation, remember this ends up being the log of 1, which is going to end up being 0. So pH is going to be equal to pKa at the half equivalence point. And like I said, this could be used to help us identify which weak acid or weak base we have. So half equivalence point should be something that you can recognize on a titration curve. Let's keep going and look at what happens whenever we have a base titrated with a strong acid. So the line in black is if we started off with a strong base and it's titrated with a strong acid. So yet again, that's kind of the mirror image of what we looked at yesterday with strong acids and strong bases. But it starts off at a very high pH. That equivalence point, whenever reached, should end up being approximately 7 in the middle of that vertical curve, and then it would end up at a low pH because we have a strong acid. Whenever we have a weak base, it is going to start off at a lower pH, so it's not going to be as basic. It is still going to have that buffer zone before the equivalence point. So in here is our buffer zone. Whenever it reaches the equivalence point, because our acid is stronger, it will end up at a pH that is lower than 7, when it reaches the equivalence point. And then it will continue to decrease over time. So looking at our overall steps, whenever we are doing the math for a weak base with the strong acid, these mirror what we did yesterday with the weak acid. But like I said, where we previously had like Ka, we're now going to have Kb and vice versa. So our initial pH, yet again, because it is a weak base, we have to do an ice table and use the Kb value to figure out how much hydroxide we're going to end up having to find that pOH, to in turn find pH. Anytime before the equivalence point, we can have our reaction that is occurring. We would get our amounts of our weak base and conjugate acid, and those would plug into the Henderson-Hasselbalch equation. Very similar to what we did yesterday with weak acids. One thing to remember is even though we're dealing with a base in our Henderson-Hasselbalch equation, it is still, to find pH, it needs the Ka value. So if you have the Kb value, you have to find Ka before plugging into the Henderson-Hasselbalch equation. At the equivalence point, we are still going to have two ice tables and two reactions like we had yesterday. So all of the weak base would react, making our conjugate acid in the first ice table using moles like we did yesterday. But for the second ice table, the conjugate acid goes through hydrolysis, reacting with the water, which would in turn produce some of our weak base and hydronium ions. And since we have hydronium, which is an acidic particle, we can use Ka in the ice table to figure out pH ultimately. And then at any point in time after the equivalence point, because we're dealing with a strong acid, we have excess hydrogen or hydronium ions. So we can simply plug those into the pH formula once we know how much is excess. So let's look at this one, and I'm going to try to fit it on this screen best as I can. I'm going to write as small as I can. But this is going to go through all 5 steps like we did yesterday with the weak acid and strong base. But for this one, we have 25 milliliters of 0.70 ammonia that is being titrated with 0.5 molar hydrochloric acid. And writing out our reaction, so we are having ammonia with hydrochloric acid. Excuse me, that's a little messy. That would in turn make the ammonium NH4 plus, and the chloride ion would be left over, is kind of what's dealing with here. Remember, you can replace the hydrochloric acid with hydronium in this case, and then that would simply leave behind water. Either way is fine, but kind of know what we're dealing with at any point in time. But this is going to be a 1-to-1 ratio between these, so that's going to be important, finding our equivalence point. So finding the equivalence point, remember we have to start with liters of our known solution. So we have 25 milliliters of our base. We can change that into moles using molarity. So liters goes on the bottom, moles goes on top. So our molarity is 0.70 moles per liter. We have to change from moles of base into moles of acid using our mole ratio, and they were a 1-to-1 ratio. And then once we have moles of acid, since we know molarity, we can continue, change from moles into liters using the molarity of the acid, which is 0.50. So if we put that in the calculator, this should reach the equivalence point at 0.035 liters of hydrochloric acid. All right, for our initial pH, remember, since ammonia is a weak base, we do need to do an ice table. So we have ammonia in water, and that will react to produce ammonium and hydroxide ions is what we would have left over. So remember, because we are going to have to plug into KB, we do need to use molarities. So we have 0.70 molar ammonia. We have nothing else initially. So our products are going to increase by X. Our reactant will decrease by X. So we have 0.70 minus X, X, and X. So if we were to look up ammonia's KB value is 1.76 times 10 to the negative fifth. That would be equal to, we would have X squared on top from our products, and we can ignore X and just use the 0.70. If we multiply by 0.70 and take the square root, we're going to get that X is equal to 0.0035 molar. And that is equal to our hydroxide value. So since we know hydroxide, we can plug into POH. So negative log of 0.0035. This would be a POH value of 2.45, which will convert into a pH value when we subtract from 14 of 11.55. Let me swap colors for the next part. I may have to erase some of this to make room, but I'm going to try to make it all fit. So that was initially, we find the pH of the weak acid just like we did earlier in the unit. If we're looking for the pH after 10 milliliters is added, this is before the 35 milliliters that is the equivalence point. So this is before the equivalence point. We have to see how much has neutralized. And remember, when we're neutralizing, we are dealing with moles. So we have our reaction. We have ammonia reacting with the hydrochloric acid, so the hydronium ion, producing ammonium and water. Remember, to find moles, we do molarity times volume. So I'll do this up top to find moles of ammonia. We have to do the molarity, the 0.70, times the liters, the 0.025. So that would give us 0.0175 moles of ammonia. For the acid, to find moles, we would have to do the 0.5 molar times the 10 milliliters, so times 0.01. So this would be 0.005 moles of acid. And we have none of our conjugate initially. So remember, the whole goal is for the acid to get down to 0. So this would decrease by 0.005. The product would increase by 0.005. And our ammonia would end up being 0.0125 moles. Oh, excuse me, I changed color. So once we know our weak base and conjugate acid, we can plug into Henderson-Hasselbalch. But remember, Henderson-Hasselbalch, we need Ka, not Kb. So to change the Ka of 1.76 times 10 negative, or excuse me, the Kb of 1.76 times 10 negative fifth into Ka, we have to do the 1.0 times 10 to the negative 14th divided by the 1.76 times 10 to the negative fifth to get a Ka value of 5.7 times 10 to the negative 10th. And then that's plus the log of our base over our acid. So our base is the 0.0125. Our acid is the ammonium, so 0.005. And this would result in a pH of 9.64. So yet again, we added acid, so the pH went down, but it's not going down at a large amount at this point in time. The trickiest part is finding the pH at the equivalence point, and here's where I may need to make some extra space. So remember, at the equivalence point, moles of acid equals moles of base. So we should end up with only conjugate acid. So our first reaction of the ammonia and the hydrochloric acid producing ammonium and water. So we started off with 0.0175 moles of base. At the equivalence point, we should have that same amount of acid. And if we started with none of the ammonium initially, these would go down to 0, and we would end up with 0.0175 moles of ammonium. Here's where we said it has to go through a second ice table because the ammonium will go through hydrolysis and react with water. So the reaction flips, and it will end up making some of the weak base back with some acid particles. Now, this second ice table, remember, because we are going to have to plug into K, it needs to deal with molarity. So we have to do the 0.075 moles. I'm going to do this in red so you can see it. Divided by the volume. So we started with 25 milliliters of base. Our equivalence point is at 35 milliliters. So 25 and 35 is 60 milliliters. So we divide by the new volume, and we get that the molarity of our ammonium is 0.29 molar. And we had used up all of the ammonia and hydronium, so those would be at 0. So our products would increase by a factor of X. Our reactant would decrease by a factor of X. So we have 0.29 minus X, X, and X. Because we have hydronium, we have to plug into Ka. And from the previous step, we figured out that the Ka was 5.7 times 10 to the negative 10th. So that's going to be equal to X squared over the 0.29, because we can ignore X there. So if we multiply by 0.29, take the square root, we get that X is equal to 1.3 times 10 to the negative fifth. And that will be our molarity of our hydronium ion, matching up with our ice table. So if we have hydronium, we can find pH simply by doing the negative log of that hydronium value. And we get that this is a pH of 4.89. So if you remember, because we have a strong acid, the equivalence is at a lower pH. For the last step, this is one where, since we're looking at the pH at 48 milliliters, this is past the equivalence point. So all of the base should have been neutralized and we should have excess hydronium ions. So we just have to figure out how much excess we have. So if we look back at our reaction of the ammonia with the hydronium, we had 0.0175 moles of ammonia. For the hydronium, we have to do the moles. That way we figure out how many moles are left over. So we have to do the 0.05 molar hydrochloric acid times the 48 milliliters. That is going to end up being 0.024 moles. And yet again, we had none of the ammonium initially. We're not even worried about the ammonium with this one. So since the base is smaller, it will go down to 0. And we will end up with excess hydronium in the amount of 0.0065 moles. Now, since we know hydronium, we can immediately find pH. But remember, pH uses molarity, not moles. So we do have to find our molarity. So the 0.0065 moles divided by the total volume. So the 25 milliliters of base plus the 48 milliliters of acid is 0.073 liters at 73 milliliters. This is a molarity of 0.089 molar hydronium. And if we plug that into pH, so do the negative log of this value, we get that this is going to end up being a pH of 1.05 at the end of this titration. So that was the same process we did yesterday with the weak acid, but this time we started with the weak base. So like I said, anytime we had like Ka, it swapped for Kb, and vice versa. One thing to think about is you guys looked at polyprotic acids previously that, remember, had multiple hydrogens that could ionize. And we said that it only ionizes one hydrogen at a time. So that's where we had different reactions for each hydrogen. Titrations for these will look approximately the same. You will have an equivalence point for whenever it neutralizes each hydrogen. So here's what a graph would look like. If we started off with here, it's down at 1, so this would be like a strong polyprotic acid. It has one equivalence point where it neutralizes the first hydrogen. And then if we continue adding base, it will neutralize the second hydrogen and then ultimately level off at that high pH using a strong base. So since this has two equivalence points, this is one of those diprotic acids. So this might be something like H2SO4 that has two hydrogens that ionize, and each equivalence point accounts for each hydrogen that is ionized. And notice that the equivalence points take about the same volume because they are the same molarity. I just wanted you to be aware of these if they come up.